Today we're starting the 7th unit of Physics 11 where we're going to talk about waves. This unit is divided into two big sections, one about the properties of waves and the other about the behavior of waves. So first off, we need to know what waves are. So a couple of questions that we'll answer in class will be how does energy move, what is a pulse, and versus what is a wave. So they're related but similar. And we'll go over that in class when we get to play with the slinkies. But what we want to cover right now are some of the other details about types of waves, which there are two broad categories. We've got mechanical waves and electromagnetic waves, and the big difference is that the mechanical waves need a medium. And now a medium is anything that has mass and takes up space, so that's matter. And so that can be water, that can be air, that can be any gas, any solid, something, but it needs those particles to move through it. So an example of that would be sound or, water waves, because they have to have water, or even earthquakes are a wave, and it needs the earth crust to go through it. Versus electromagnetic waves, which do not need that medium, they can just travel through space regardless of the particles that are around them. And examples of those would be anything in the electromagnetic spectrum, which include visible light, microwaves, radio waves, X-rays, gamma rays, infrared, ultraviolet. And so those don't need the matter to propagate. They can propagate through space without the medium, which is very good because going through particles slows you down, which is why electromagnetic waves and light travel as fast as possible, which is the speed of light. But we're going to study this unit on mechanical waves. We'll talk about light in our next unit, Unit 8. So in mechanical waves, you can have different types. You can have transverse waves, longitudinal waves, surface waves, and torsional waves. Surface waves are a combination of transverse and longitudinal. We're not going to cover the surface waves. And torsional waves are when you're twisting something back and forth. And again, we do not cover that in this. We are going to focus on a transverse wave and a longitudinal wave. And transverse versus longitudinal is easy to distinguish. Transverse are the ones you see that move perpendicular to the way that the line goes. So by perpendicular, it's going to look like this. So it looks exactly like a wave. It goes up and down and the wave moves across the page. Whereas a longitudinal wave, those vibrations are parallel. So you've got something that is tightly wound together that spreads out and tightly winds again and spreads out and tightly winds. And so there's a compression that moves through the air in the direction of the waves going. An example of that would be sound is a longitudinal wave. An example of a transverse wave, where it's moving perpendicular, would be water ripples. And so if you just throw a rock in a pond, you see the ripples flow out from where the rock goes in the water. Those ripples move up and down, though the wave is moving out. So they're moving in perpendicular directions. Transverse, longitudinal waves. But regardless of whether it's a wave or anything else, if you have any repeated motion, you have some certain characteristics. First off, one cycle. For a wave, such as a transverse wave, that would be from one peak or crest to the next peak or crest. But that could be anything. It just depends on what the repeated cycle is. So if you think about an orbit of a planet, one cycle would be like 1 year, where the planet goes all the way around to the other side. A period is how long it takes to do that cycle. So again, making the analogy of rotating around the Earth, that repeated motion, that time would be 1 year to do that cycle. Whereas for a wave, we might be talking about a couple of seconds, or even as few as a couple of nanoseconds to do one cycle. With most waves, you also have an amplitude, so how far the wave disturbs those particles. So that's why we're talking about mechanical waves here, disturbing the particles from their normal place, either perpendicular or parallel. How far they move would be called the amplitude. A wave with more energy moves the particles more. That doesn't mean it goes faster, it just moves the particles farther away from their rest position, but they eventually come back down. And that would be our amplitude, so that's measured in meters. And frequency is a number of cycles that happen in 1 second. So it's kind of like the period, where that's the time for one cycle, but this is the number of cycles that occur in 1 second, and that can be either a full cycle or less than a cycle or multiple cycles. One number you might hear of is 60 hertz, and that's, the frequency, or 1080p at 60 hertz. That means that the TV screen is refreshing itself at 60 times every second to show you that image and to see the video. So that's 60 things in 1 second. So again, a repeated motion, and these terms apply in many different areas of physics beyond just waves. Wavelength, we have the length of the cycle measured in meters, but this is the only one that's, has a different symbol, and it's a Greek letter lambda. And it kind of looks like an upside down Y. It's got a little bit of a tail on the top of it. What's important, though, is knowing how to use all of this stuff and how to relate them together. So first relation we're going to use is the frequency and the period. And they are related as the frequency is 1 of the period, or this could be written as the period is equal to 1 over the frequency. So if you have the math game, you know that this would mean they are reciprocals. So moving along to our first example, we've got an electricity grid with an alternating current, so it propagates an electrical wave with a frequency of 60 hertz. So how many cycles does that mean per second? So back to the definition of frequency, that's how many cycles in 1 second, so that means our answer is 60. And what is the period of this wave? So if the frequency is 60 hertz, we're going to calculate this as t is equal to 1 over the frequency. So we have 1 over 60 hertz, and that will give us 0.0, 2 seconds to proper sig figs. It'd be the number's 1.666666666 in your calculator, but to proper sig figs, because 60 hertz has 1, we'd get 0.02 seconds. Now, to do some diagrams, we got to know how to label these things, what they actually represent. So we've got this transverse wave. We need to label these things and do a bit of measurement. So, cycle and wavelength, they're going to be labeled as the same thing. So we've got cycle and wavelength. And I also have to measure the wavelength, which I just did using a ruler. And on my screen, that was about 4.7 centimeters from the one peak to the next. But it's a peak of a curve, but it actually has a proper name, which is the next term there, which is a crest. And then a trough is when it's displaced to the bottom. So we've got crest and trough. Now rarefaction and compression don't relate to a transverse wave, so we'll leave that for the longitudinal. And then our last thing is an amplitude. So the reason this dotted line is here is to show our rest position, which would be right in the middle, so we get our amplitude measured from that, and I would measure that to be about 1.5 centimeters. Now, to calculate the frequency, if I think of this picture as happening in 1 second, in that there's 1, 2.5 full cycles. So that means there's 2.5 cycles per second. So our frequency is 2.5 hertz. And to calculate the period, I do 1 over 2.5, and that would give me, and that's going to give me 0.4 seconds for my period. So do the longitudinal wave and pause the video and come back in a couple seconds and you'll see the completed version. So here's the completed longitudinal wave where we've got the rarefaction, the compression. The compression is when the particles are together, and the rarefaction is when they're spread apart. Kind of like the crest and the trough, but it's a different direction, so they can't be called the same thing. So there's no crest and trough in a longitudinal wave, and there's also no amplitude because it's just much more difficult to measure an amplitude when it's not being displaced in a perpendicular direction. But we still have our wavelength, which I've drawn from one compression to another because that's the easiest to visualize. And so I measured that to be 4.3 centimeters. And the frequency, if I count how many cycles I have, I see 3 complete cycles. So I have 3 in 1 second, so a frequency of 3 hertz. 1 divided by that gives me a period of 0.3 seconds. Now if we compare this bottom transverse wave to the one at the top, what you want to think about is anything that has changed, and we'll go over that in class. Speed of the wave. So one last thing, we need to talk about how to calculate the speed of the wave. Speed is always calculated as distance over time. But if we're going to think for one cycle, the distance that it would go in one cycle would be equivalent to the wavelength lambda, and the time for one cycle would be the period t. But physics, we don't want to use that t because t pops up a lot, so we actually replace that with frequency. So we get the equation v equals lambda f. And this is known as the universal wave equation, where the speed in meters per second is equal to lambda, the wavelength, in meters times the frequency in hertz. And so here's an example of using this in a calculation. So a sound wave has a frequency of 192 hertz and travels the length of a football field in 91.4 meters in 0.271 seconds. What is the speed of the wave? What is the wavelength? What is the period? And what if it was all changed? So speed of the wave, now in this case we're told how far it goes in a certain amount of time. So we can actually go back to our original equation for speed by plugging in distance over time, and we would get to 3 sig figs, 337 meters per second. Now that we want to figure out the wavelength, we can actually go to our universal wave equation, which is v equals lambda f, which we want to rearrange for lambda as v over f, and so we can calculate lambda using that as 337 divided by 192, and we get about 1.76 meters for our wavelength. So this is a pretty long wave. And period, now period is going to be calculated as 1 over the frequency, and so that would give us 1 over 192, which is going to be a very small number, 0.00521 seconds. Now if we change that to 442 hertz, a few things would change, but some things would not. Most importantly, changing the frequency does not change the speed of the wave. So a sound wave in air would still have the same speed, which is 337 meters per second. So we can calculate lambda, the same as we did in part B, using v over f, but our new f and lambda in this case would actually be 0.763 meters. And our new period for 442 hertz would be 0.00226 seconds. So we have a shorter period and a shorter wave with it, but it happens much more often in a second because of that. And so we have an increase of frequency. Frequency is sometimes hard to distinguish from speed, but that's where the equation comes into play. So that's the properties of a wave, and as always, physics is awesome.